What's good, YouTube? Today we're going over question 2-1 from the Hebler Statics textbook. This is in chapter 2, so let's get right into this. We're going to be solving it first through the method of components and second through the parallelogram method. So if you would like to skip to that, then please do so. So first off, method of components, so 2-1. If theta equals 60 degrees and F equals 450 newtons, determine the magnitude of the resultant force and its direction, measured counterclockwise from the positive x-axis. So already I can tell you this angle that we're finding is going to be from the positive x-axis. So on this side, the side without the symbol x is always negative. So it's going to be right here, something like that. It's going to be this angle in which we're solving for. So we know it's going to be over 90 degrees. And we know that F, our resultant F, is going to be a summation of both this force here and this force here. So here you can see our restatement. That's basically just a restatement of the problem statement. Then your givens. So here we have theta, which is 60 degrees, and F, which is 450 newtons. And some professors actually change, what I've noticed, some professors change the numbers up at the top, so yours may be different. Just keep an eye out for that. But regardless, you should still be able to follow and get the right answer and understand what's going on. Also, for the givens, you could put the 700 Newton force down here in its angle if you wanted to do so. And then your finds, you're going to want to find the resultant force, Fr, and its resultant angle from the positive x-axis, theta r. Our assumptions, static and rigid body. It does not move, and it's not going to bend or break. So we're going to find the fx and fy components for each one. Use a Pythagorean theorem to find Fr, which you'll see how that works out. Inverse tangent formula to solve the angle between the force resultant and the negative x-axis. And then finally, we'll want to use some geometry skills and some common knowledge to find the angle between our force resultant and the positive x-axis. And the solution, obviously, we're about to find that out. So first off, we want to sum both of these forces. We want to sum their magnitudes. We want to sum their x components together, the magnitudes of their x components. Then we want to solve their y's separately, because the only way to add 2D vectors is to sum them by their x and y components. So basically, let's say this force right here, F, we want to break it down to its x component, which lies horizontal here, and its y component, which is vertical. And the same goes over here. I won't draw that though, I don't want to make it too messy. So we want to find the x component. First, let's start with our F over here, our 450 newtons. This is 60. Okay, so we know the magnitude's 450. And basically, to find the x and y components, you always copy down the magnitude, and then you use a specific angle that's dependent on whether you're trying to find y or x. So this is newtons. So we're going to be using cosine of 60 in this case because we're using x as our reference axis. And we have the angle, basically because we have the angle that attaches to F and attaches to x. Look at it that way. So basically our force's angle attaches to both the force and the x. So let's say it attaches to the y and the force. So this is 30 degrees. We know this is 30 in here, right? Because there's 90 degrees here. If you were to use the 30 here, which you still could, you'd want to use sine. So once again, if you're using x as your reference angle, solving for the x component, okay, only when you're solving for the x component, you want to use cosine. And when you're using y as your reference angle, solving for the x component, you want to use sine. So it's basically the opposite of what you normally use. But I would always recommend using the angle between the force and the x-axis, not the y-axis. Unless this 30 was given here, then I would recommend using it or solving for the 60 here. You could do either way. But enough bantering. We got cosine of 60. Or again, this could be sine of 30. And that's going to be positive because this is pointing in the positive x direction. Our next one, as you can see, negative. The x is in the negative direction. So we write, again, our magnitude 700 newtons, then our cosine of 15 degrees. You sum those together, and we get the sum of our forces in the x direction come out to be negative 451.15 newtons. That's primarily because this force here is so much larger in comparison to this, especially because it almost lies entirely on the x plane. So now solving f of y, once again, we're going to copy down our magnitude of our force, so 450 newtons. And this time, if we're using 60 as the reference angle, it's going to be opposite. Everything is basically, the easiest way to think of it is it's opposite when you're solving for y, or opposite if you're solving for x, whichever reference you want to use. So sine of 60. Again, if I was to be using this 30, it would be cosine of 60, because then I'm between the axis we're trying to solve for and the force. Whenever it's the direction you're solving for and the force, whenever you're using the angle between those, that's when you use cosine. And when it's the opposite, such as in this case, because we're using the angle between the f and the x, it's going to be sine. It's going to be the opposite function. So awesome. That is going to be positive because it's going upwards. And the next one's going to be negative because you guessed it, it's going downwards. And once again, that's going to be sine of 15. It would be cosine if I used 75 right in here, attaching to the y-axis. So then you plug that guy in your calculator, and we're going to come out with 208.4 or 54, excuse me, newtons. So now basically what we solve for here, real quick, you can see here what we did to the f. We broke it down into both its x down here and its y components, and you can see those appropriately right here. And then what we did was we did the same with the 700 newtons. I won't draw it just to keep it tidy over here. And we did the same with the 700, and then we added them together, which creates a new triangle because we added the x and the y separately, which gives us a new horizontal and a new vertical direction. So our new horizontal direction looks something like that, and our new vertical looks something like that. And as you can see, there's a hypotenuse here. The hypotenuse is a sum of the f of x and the f of y coordinates. And you may have guessed it already, but the hypotenuse is actually our resultant force. This is our FR. Because we have summed both of these forces and found their x's and y components together. And then if we just solve for the hypotenuse this triangle creates, we find our magnitude of the force and also the direction. And if you notice, this is a right angle triangle. We know both sides. We need to solve the hypotenuse. That is a recipe for the Pythagorean theorem. So c squared equals a squared plus b squared. And I'm going to revise this a little bit. So first off, we're going to get c all alone. So we're going to square root both sides. And that cancels here. And then we're left with c equals that. So our c is actually going to be FR. So let's write FR. And that's going to be equal to both our x squared and our y squared component. So 451.15 newtons squared. I'm keeping a lot of sig figs here. And you might be wondering, okay, why do you turn it positive? Well, because if you multiply a negative by a negative, it becomes positive. And here we're squaring a negative, basically multiplying the number by itself, making it positive. So 208.54 newtons squared. And that's going to give us a fresh new answer. And our force resultant is going to be larger in this case, and it comes out to 497 newtons. So now we are going to want to use the tangent inverse equation. I'm not going to explain quite how it works in this video. I will make a separate video for that, but basically this function allows us to find the angle right in here. It allows us to find the angle between the x component of our triangle and our hypotenuse. Awesome. And basically, to type in your calculator, you want the function inverse tangent, so tangent -1, and that's going to be a function on your calculator. It better be, or else you need a new calculator. And then you want rise over run, aka y over x, aka the forces in the y over the forces in the x, and that's going to be the sum of those. So in this case, to find the angle inside our newly found triangle, we're going to want Fy, so rise, 208.54 newtons over 451.15 newtons. Our units cancel, and this is going to be degrees, and that comes out to 24.8 degrees. And you can keep the negative on the 451, or you can get rid of it. As long as you know what you're solving for, it doesn't really matter. The negative is arbitrary. If it comes out negative, you know what you're solving for. Awesome. So we found this guy right in here. Let's call it like that. Let's call it alpha. Awesome. So that's what alpha equals. So now we want to find this whole angle over here. We want to find all of this, right? We want to find the direction measured counterclockwise from the positive x-axis. So as you can see here, that's counterclockwise, and that's the positive x-axis on this side, far away. So as you can see, this whole thing is actually a half circle. A full circle is 360, and a half circle is 180 degrees. And another way to think about this is that each quadrant, so let's say right here is a quadrant, right here is a quadrant, we know that. There are 4 quadrants here. Each quadrant is 90 degrees, so confirmed this is 180, this whole stretch. So if we know the angle inside the triangle is 24.8, right? To find the remainder, all we have to do is subtract 180 minus 24.8. And it's that simple, it really is. So let's say we're solving for theta 2, or theta r, excuse me, that's our resultant. That's going to be simply 180 degrees, my bad, minus 24.8 degrees. I will rewrite that. So our theta r, once again, is equal to 180 degrees minus our 24.8 degrees. That's going to come out to 155.2 degrees. Awesome. And that is our resultant angle relative to the positive x-axis. And this guy right here is our resultant force. So 2-1, using the parallelogram method. If theta equals 60 degrees and F equals 450 newtons, determine the magnitude of the resultant force in this direction, measured counterclockwise from the positive x-axis. So like with the method of components, we are going to solve this guy right here, this angle. This is going to be our theta r, and we're solving for that. That's going to be our resultant. Counterclockwise, again, that's counterclockwise. You can look at your clock right now to confirm it. And then this is the positive x-axis. Wherever the easiest way to remember it is, first off, it's pretty standard that up is positive and right is positive as well, and the opposites are negative. But also you can look at wherever they have the x's and y's labeled. That's typically where the positive is. So before you do anything, you want your engineering paper. Restatement copied down, givens copied down. The finds, we want to find FR, our force resultant, and our theta resultant, our angle resultant. Assumptions, not going to move, and it's not going to bend. So for the parallelogram method, we're going to want to copy the image and forces to create a parallelogram. So something like this over here, I'm sketching. Something like that. You have to keep both the angles, at what angle they are, and the length of them to create a parallelogram, which is very convenient. We'll show all the advantages of that. And then you want to solve enough angles using geometry to use a lot of cosines to find FR, use a lot of sines to find the interior angle, and then we're going to use some geometry to find the angle referencing the positive x-axis. So let's get right in. I have conveniently made us an awesome parallelogram here. That was clutch. So look at this. This guy right here is going to be our 450 newtons, and you can label the magnitude of the force as the length of the side. Works that way. 700 newtons here. Awesome. And then we know this interior angle here is 15 degrees. And then we know that theta over here is 60 degrees. Put it right here. I'm gonna write somewhat small just so I can fit everything in here. And then because we know this is 60, we could already find this because we know there's 90 in one quadrant, right? There's 180 in both, 90 in one. So because there's 90, we just subtract 60 and then we can get 30. So let's expand on this. This is 30 degrees. And then look at this. This entire quadrant is inside the parallelogram. So we know this is 90. Awesome. So we know this entire angle all of a sudden inside the parallelogram. Would you look at that? So 90 plus 30, okay, right? That's 120 plus 15, so 135. You know this entire angle in here is 135. So cleaning that up, this whole angle inside 135 degrees. Awesome. And because these forces here, let me actually write the magnitude of these forces as well. 450 newtons here, 700 newtons here. Because these are the same, The angles are the same, the magnitudes are the same. This side is also 135. Same magnitudes of the sides, same angles. Everything's identical on both sides. So 135 here. And then because we know these two angles, and we know that these angles are identical on either side here, we can solve for these angles. There are 360 degrees in a three-sided or a four-sided figure, excuse me. So we already know there's 135 plus 135, which comes out to 270. So to find these angles, let's just say theta 1 and 2. These are going to equal 360 minus 270, which is again 135 plus 135. And that's going to give us 90. And then if you divide that by 2, because we have two angles that are absolutely identical, so they're going to split the remaining 90 degrees evenly. So divided by 2, and then we get 45 degrees. Awesome. Now we're set. Now we can start doing the real math. So that was kind of geometry heavy. You just need to know the anglage in a quadrant, and that this side was equal to this side, and that these two sides were equal as well, and how many degrees total are in a four-sided figure. So now I deleted the 135 on each side because we, quite frankly, don't need them anymore, and I'll show you why. First off, do you know where the force resultant is going to lie in a parallelogram like this? Because I will show you. If you watch the method of components, you will already know generally where it is. But watch this. It comes out right here, and it most conveniently attaches to the opposite side. I'm sorry, that's a little to the left. It comes right here. It basically, the tail and the tip both touch the intersections of the forces, okay? And once again, the parallelogram method can only be done with two forces. If there are more than two, you have to use the method of components. But in this case, obviously, because there are two forces, you can go ahead and do this. So we know this is our FR. That is awesome. And if we look over here, you may have already seen it, but the law of cosines can be used now. Okay, look at this. Do you see this triangle? We have a triangle formed. So now, if you notice, we have side-side angle. Impossible to solve the law of sines. There's no way, because both of these sides do not have a corresponding angle, and this angle does not have a corresponding side. In fact, it's what we're trying to solve for. But we can use the law of cosines, and I'll show you why. So law of cosines, if you remember, it's basically the Pythagorean theorem at first, for a couple of reasons that you'll learn in Calc 3 if you take that. So c squared equals a squared plus b squared minus 2 times a times b multiplied by the cosine of c, the angle across from side c. So the side c is what you want to solve for. That's going to be our FR. Our a can be 450 newtons, our b can be 700 newtons, and what you really need to use the equation is the angle or the side across from that of which you're solving for. So here we have 45 degrees. We can plug this in for big C over here and solve for little c, aka FR. So let's do just that. So first off, we want the square root, or this square out of here, excuse me. So we're going to square root both sides. Awesome. And now we're going to plug in a lot of numbers to a cramped equation. So C, actually let me just put FR right here. So force resultant equals, because C is our force resultant, equals A, so we said 450 newtons was A, plus B squared, which is going to be 700 newtons, minus 2, multiplied by A, again 450 newtons, and B 700 newtons, and then multiplied by the cosine of our angle across from the side we're solving for, cosine of 45 degrees. That's why we needed to find the 45 degrees prior. You don't necessarily need to know you have to solve these angles before you approach a parallelogram method problem. You just have to know how to solve many angles and just go ahead and solve them. The direction to find the answer will be clear. Just know that in every parallelogram problem, you have to use a triangle like we made here. You almost always have to use a triangle, and either the law of sines or the law of cosines, or sometimes both, like you'll see here, and then some other geometry rules to end up solving your problem. So this is all square rooted here. Awesome. And then yes, that will give us our answer. And like with the method of components, we get 400 newtons. Most students always struggle on this method. It requires a lot of basic knowledge, a lot of formula knowledge, and a lot of fundamental review overall. So now we have the force, so now we need to find the angle. So what we're going to do here actually is we're going to find this. We're going to find this angle here. We'll call this alpha. And the way we're going to find this is, look now, we have our force resultant. We know this right here is 497 newtons. Don't even look at that. That is across from 45 degrees. Our 450 newtons here is across from our alpha, this angle we're going to solve for. And you might be wondering, why are we going to solve for this angle? This angle is critical to helping us solve the angle relative to the positive x-axis, this guy over here, right? Because if we solve this angle, and we know this in here is 15, like it shows over here, you see that? We know this is 15. We can subtract this from alpha, giving us this this amount of anglage here, and then subtract that from 180, the sum of two quadrants, right? Reaching to the positive x here, boom. Subtract this from 180, and then you're home free. So you can also solve for this angle up here, and then use the 180 degree in a triangle rule to solve for this angle as well. But we're just going to go right to the angle. So because we're solving for an angle, we're going to want to use the law of sines here. We have opposite, opposite. Basically, we're going to want to use the equation with the angles on top. So sine of alpha, I have a hard time writing that, all over our 450 newtons. And that's going to be equal to the sine of 45 all over our 497 newtons. So here we're going to want to multiply whatever side we're trying to solve for, right? We're going to want to multiply by the denominator to get that all alone. So we're going to multiply this by 450 newtons. This is going to cancel out. So now we need to multiply this side by 450 to make everything even. Then I recommend going ahead and plugging this side all in your calculator to get sine of alpha equals to all this. And when you do that, you're going to get sine of alpha. Let me just put a shield here. Sine of alpha is going to be equal to 0.64 degrees. So now what we need to do is get alpha all alone. So like we did here, we did the inverse of divide, we multiplied. Now we want to do the inverse of sine, which just so happens to be inverse sine. So we're going to want to inverse sine this side. So we're going to get sine to the -1, and sine inverse sine is, you guessed it, 0 or 1. It cancels out. Then you're going to want to inverse sine this side. So basically we're going to get alpha, I'll make another little wall, equals sine inverse of this guy, 0.64 degrees. And when you plug that in your calculator, you should get 39.8 degrees. Awesome. So now we have this angle inside right here. So now if we subtract the 15 out, so I'm going to find some space up here. Just follow me up here, right? We're going to want to subtract 15 out. So 39.8 minus 15 degrees equals our 24.8, in which we got from method of components, because that's going to be this guy right here, right? And then we have this, so we know this whole thing, both of these boxes together are 180 degrees. So if we just subtract this out of 180, then we can find this right here, which is what we're solving for. We want to find this. That's our angle resultant relative to our positive x-axis. So now we have 24.8, so we just simply subtract that from 180 degrees. Oh, whoops, my bad. Then we're going to end up with 155.2 degrees. Okay. So thank you so much for watching. I really hope this helped you. Give me some feedback and let me know, if there's any way to change this to make it a little better. Your feedback would mean a lot. Please like, comment, subscribe. That would mean a lot as well. And most importantly, have an awesome day. Thank you.